for Dr. Vondrak. Looking at the 35-degree Kelvin temperature you're seeing, is this what you expected? Is this colder than you expected? And can you give us some comparisons elsewhere in the solar system that we figured, Neptune or Pluto or the like? And I have a follow-up.
Sure. Well, when you say what's expected, it really depends on how detailed the model is that you do to generate a prediction. When we say what's expected and saying that this is remarkably cold, it's because the early modeling that was done of the permanently shadowed regions and their ability to retain volatiles said they would have to be colder than probably 50 to 70 degrees Kelvin. And so the expectation was that it would be desirable for them to be that cold. Now the early results from Diviner are that indeed during the daytime they get no warmer than 35 Kelvin, which is really good news if you're trying to identify whether there could be volatiles there or not. Now, what the Diviner team is in the process of doing is trying to develop a really advanced model of what the temperature would be in a PSR, a permanently shadowed region, based on illumination conditions, and then they're going to compare their model results from that with their own observations, and that work is in progress, and we hope to see that result sometime over the coming weeks or months. Was there a second part to the question?
Yes, there was a second part. The second part was comparing this to
other. Yes.
You said this is the coldest temperature we've found in the solar system. What's close? What was the colder temperatures? I mean, how would this compare to Neptune and
David
Pluto?
Page.
And while I have you here, can you explain for sort of laymen why it's important? The importance of volatiles in the permanently shadowed region.
Okay. Comparing it to other parts of the solar system, David Page, the principal investigator on Diviner, has modeled temperatures of Pluto, for example, and he has a press release that's coming out this afternoon, and there's more information, more data than I showed you in the time I had, more maps of the temperature distribution in the South Polar region on the Diviner webpage, which you can get from the NASA.gov webpage. And his conclusion is that indeed the lunar South Pole is among the coldest parts of the solar system and may be in fact colder than what we expect from places like Pluto. And the significance of volatiles, well, it's twofold. One is from a science point of view, we'd like to understand what the volatile history of the solar system is, how materials like those kinds of gases reach the moon, reach the Earth during the early history of the Earth, which is now lost, but may be preserved in the lunar permanently shadowed regions. There may be a record there of impact strikes by comets or other events in the history of the moon. So indeed probing these regions could have value in a similar way as we explore the ice cores from Antarctica and the cold regions of the Earth to understand parts of the history of the Earth. And from a resource point of view, if we want to go back to the moon and send explorers there, being able to extract materials such as water, which is going to be very expensive to import, it'd be very useful if we could find a resource on the moon that would be useful.
Okay, we have another question. Please ask your question.
Thank you. Andrea Thompson of space.com.
Mm-hmm.
Hi, yeah, I guess this question would be for Dr. Vondrak as well, but whoever best to answer it. I was wondering how big in advance these detections of hydrogen are on previous ones, or are they just sort of confirming what was already known and suspected, and what exactly is needed to figure out where this hydrogen signal is coming from, what's causing it?
Okay, the hydrogen result that we show, and it's a preliminary result from LEND, shows that hydrogen is not only in some of the shadowed craters, but also may be more widespread at the lunar South Pole. And we have to get more observations in order to really identify the significance of this and what the interpretation of it would be. We also want to understand, why some permanently shadowed regions might have hydrogen and why may others do not have hydrogen, if that's indeed the case. And the power of LRO is that we're not just sending one instrument like LEN to search for hydrogen. We're characterizing fully the South Polar region. We have the topographic maps, which give us information about the roughness and the shapes of these permanently shadowed regions. We have the temperature maps from Diviner that actually measure the variations in the temperature. Right now we're approaching summer in the lunar South Polar region. In late October is when we have the summer solstice, so we expect that the temperatures will increase somewhat in those regions, and we'll, over the course of the next year, look at these mild seasonal variations. And then we have LAMP and also Mini-RF to look at signatures of hydrogen or water in other ways. So by the end of this mission, we will fully characterize and get the best possible information we can about the occurrence of hydrogen and water in the South Polar region. The best you can do with a remote sensing satellite. But I should add also, if you want to really find out what's below the surface, you have to touch the surface and go there. And October 9th, LCROSS will impact the surface. It will do its excavation, and we'll hopefully learn more about what the content of the subsurface material is, at least in Cabeus A.
Yeah, I'd like to add just one thing, and that's...
Thank you. We have a question from James Dean of Florida State.
Thank you. I have a few questions. The first I think you just answered, but just to follow up on the LCROSS upcoming impact, it sounds like, and I think you said this before the mission as well, but you really couldn't, the LRO would not likely be able to prove any much more concretely the existence of water ice with its instruments. You would have to, you'll need LCROSS in order to make that kind of finding. Is that correct?
Well, we have many different eyes looking at the moon, and LEND is sensitive to hydrogen. It doesn't determine the form of hydrogen, whether it's in hydroxyl or methane or ammonia or just how it would be under the surface, whether it's in form of water or not. But I'm not quite sure what point you want me to make, or what question you're asking.
I'm sorry, I guess I was just trying to understand if there was a possibility of, even if you did not have LCROSS approaching with its impact, how much closer LRO could get to answering that question, even if there was no LCROSS to impact to observe.
Well, we have remote sensing instruments, and they're going to tell us an incredible amount about the characteristics of the lunar polar regions. LCROSS is an added bonus to the mission. It will do its impact and its excavation, and I think we'll be able to tell you by the end of this mission a lot more than we ever knew before.
And of course, the part of the answer is based on what LRO is going to be able to find with its instruments. If, let's say, for example, there were water present, it depends on the form of the water and where it's located. For example, the LAMP instrument, the Lyman Alpha Mapper, is sensitive directly to water, but it's only water exposed at the surface. So if there were significant levels of water exposed at the surface, for example, as a surface frost, we would get a signature for water. The nature of the question indicates how tough of a problem this is.